the simplest and honestly most practical way to prepare a buffer solution if you have either a weak acid, a weak base, or the salt of a conjugate acid or the salt of a conjugate base is to just grab one of those, okay, and then mix it with either a strong acid or a strong base, because that reaction will produce the appropriate conjugate weak acid or conjugate weak base. Well, that being said, of course, you're not going to mix a lot of hydrochloric acid or sodium hydroxide to base and an acid respectively. Okay, but let's try some problems wherein that's actually used. I've done this myself when I was working in a pharmaceutical company after I graduated from college. So basically, we're just given like a solution of acetic acid, and then we're going to add NaOH to just produce the acetic acid sodium acetate buffer. But for this one, let's try, how about if you're given sodium acetate and someone tells you, okay, make a buffer and here's some hydrochloric acid gas or hydrogen chloride gas. Okay, so let's try each scenario. Okay, now again, so here we're actually looking at sodium acetate. Okay, sodium acetate. And again, as always, the only basic component of sodium acetate, okay, is just the acetate ions. Okay, so sodium acetate in aqueous solution will break up into sodium and acetate ions, and again, the acetate ion has basic properties. Now, upon the addition of hydrochloric acid, sodium or acetate from sodium acetate will actually react with HCl, okay, to produce, well, it will react with the proton from HCl, because the chlorine again is not acidic in HCl, okay, to produce acetic acid. All right, so if you actually add, remember again, add hydrochloric acid to sodium acetate, or to the acetate ions that is, you will form acetic acid in a 1:1 fashion, meaning 1 mole of the acid of H plus will react with 1 mole of acetate ions to form the acetic acid. Okay, so let's see the following conditions. What if you were to prepare a solution which is 1 molar of sodium acetate, and let's say the first case is pH is equal to pKa. Okay, problems like this, let's just first assume a volume that we want for the solution. I like working with 1. So let's just say that, assume here we're all working at a target volume of 1.0 liters. Okay, so that's our target volume. If you want 500 ml, go for it. Okay, now at pH is equal to pKa, remember that that is the scenario, okay, at which log of the conjugate base, which is for this case the acetate ion divided by the concentration of acetic acid. Okay, so this ratio should actually be equal to 1, and the log of 1 should be equal to 0. Okay, so what I'm trying to actually say here is if, let's say for example, we're targeting to prepare 1 liter of solution, and we have 1 molar currently of currently 1 molar of sodium acetate. Now, since we're adding HCl as a gas, let's just ignore changes in volume. Okay, ignore changes in volume. Okay, but basically what we have right now is 1 mole of acetate ions. How did I figure that one out? 1 molar times 1 liter. Okay, 1 molar times 1 liter. Okay, but if we re-express this one, we have covered this in lecture. Well, if you're watching this right now, we have covered this in lecture already. We can re-express this one actually as this thing as the moles of CH3COO minus acetate ions, okay, divided by 1 liter. Okay, so I just basically broke up this molarity expression into moles and volume, divided by the moles of acetic acid, okay, divided by 1 liter. Okay, and we did say that a number, the only number which will give you a log value equal to 0 would be 1. So this one should be equal to 1. Now I can cancel out 1 liter because they appear on both the denominator of the numerator and the denominator. And in the end, what I will actually just get will be the moles of CH3COO minus should be equal to the moles of CH3COOH as acetic acid in solution. So again, what this means is the moles of sodium acetate that will be left as a consequence of hydrochloric acid, well, in its gaseous form, hydrogen chloride, reacting with acetate ions should be equal to the number of moles of the acetic acid that will be formed. Now, since we're actually starting here with 1 mole of acetate ions, okay, the only way, the only number of moles in which this will be true true, that's not how you spell true, of course, is if those two are equal to basically both 0.50 moles. Okay, so if both of them are 0.5 moles, then this term basically, which we have established earlier, will cancel out. They'll have also an equal molarity, 0.5 molar divided by 0.5 molar if you're not convinced, and therefore pH will be equal to pKa. Now, in order to produce 0.5 moles of acetic acid, we have again established before that when we have acetate ions, okay, I regret removing that equation, react with protons from HCl, okay, it will produce acetic acid in a 1-to-1 fashion. So therefore, if we actually needed 0.5 moles of acetic acid with 0.5 moles that is of sodium acetate, then that must mean we have to produce this much of acetic acid from 0.5 moles of hydrogen chloride. So here, basically the answer is you must add 0.5 moles, or 0.50 if you're particular with significant figures. I had 0.50 moles of hydrogen chloride. I'm saying it hydrogen chloride because it's a gas. Okay, and to make the buffer with a pH equal to pKa. Okay, so that's pretty simple for that problem. Now, what if you have, for example, a target pH of 4, and again you want to start with sodium acetate and just add hydrochloric acid to produce acetic acid. Okay, so for this one, let's actually write the conditions. So for this problem, we actually wanted a buffer with a pH of 4, okay? And we can write that in the Henderson-Hasselbalch equation. So pH of 4 is equal to 4.74, okay, plus the log of acetate ions, CH3COO minus, and its conjugate acid, CH3CO, OH. Okay, so if we actually do the math, we're going to get here 0.74. 0.74. Actually negative, we're just bringing this over to this side of the equation, is equal to log of the ratio between the base, okay, and the acid, and the ratio between the base and the acid will just be CH3COO minus divided by CH3 COOH is equal to 10 to the negative 0.74, which is just equal to 0.18. Okay, now from here, again, remember that we can re-express this based on our arguments earlier. I don't want to rewrite it anymore, but we can express this as number of moles divided by number of moles. Okay, so here, therefore, again, this should be the ratio also of the number of moles of sodium acetate. Oops, that's not how big a negative sign should be. Then divided by the number of moles of acetic acid. This should be equal to 0.18. Okay, so therefore, what this actually means is the ratio of sodium acetate to acetic acid should be 0.18, or the number of moles of sodium acetate should be equal to an 18th, not an 18th, I guess, but 1800ths, there you go, of the moles of acetic acid. Okay. Now, keep in mind that the only source of acetic acid, okay, the only source of acetic acid is the only source of acetic acid is the acetate ion. Okay. Okay. So therefore, if you have a total of 1 mole of acetate ions to begin with, which is again given in the problem, 1 molar and in 1 liter, okay, then you can write that the number of moles of acetate left, okay, left after sodium acetate reacts with H plus from hydrochloric acid, after reaction of 1 mole with H plus, okay, plus the number of moles of CH3COOH produced, which is again after the reaction of 1 mole of acetate ions with H plus, should be equal to 1. Okay, and these numbers, okay, these variables are actually these variables as well. I mean, they should not be the beginning concentration, otherwise the number of moles of acetate or acetic acid should be 0, okay, which makes no sense. So if those are the numbers, then we can actually substitute this equation. The number of moles of acetate is equal to 0.18 moles of acetic acid, okay, or 0.18 times the moles of acetic acid. So our equation therefore becomes 0.18 moles of acetic acid plus a mole or plus n, or number of moles of acetic acid. Okay, so it's basically, let me just use a different colored pen. It's basically this, okay, and then this one is just that, and then we just equate it to 1. Okay, and then what will that give you is if you add these two together, you'll have n number of moles of acetic acid is equal to 1 divided by 1.18. Okay, you have to divide both sides of the equation by 1.18, and then what you'll get is 0.85 moles of acetic acid needed. Okay, and again, since we established earlier that how much acetic acid is produced is equal to the number of H plus ions that we need from HCl, and therefore to produce a pH of 4, to make a buffer at pH 4, then you need to add 0.85 moles of hydrogen chloride as a gas. Okay, usually it's a gas, by the way, again, so that we can assume no volume changes. Otherwise, our problems or our equations will not be, I guess, as straightforward as this. And then lastly, what if you want to make a pH 5 solution? Okay, so for this one, again, we start with the Henderson-Hasselbalch equation. Okay, so 5.0 is equal to, again, the pKa is 4.74. Okay, plus log of, and again, and for this time, again, since we have proven this to be again equal to this one. I'm just gonna put there the number of moles in the Henderson-Hasselbalch equation. Now again, warning, that is true because we're only working with a solution which does not change in volume. Okay, so this one should be log of the moles of acetate, okay, divided by the moles of acetic acid produced. Okay, acetate remaining, again, divided by acetic acid produced. So this one will just be 0.26, okay, log of the ratio of moles, okay, N of acetate divided by N of acetic acid, okay, which will just give you 10 to 0.26 is equal to the number of moles of acetate divided by the moles of acetic acid, which is just equal to 1.8. Okay, so 1.8. And again, here, from here, you can actually rewrite this equation as 1.8 times the concentration of acetic acid should be equal to the number of moles of acetate ions. Okay? And again, since both of these should have come from 1 molar of unreacted sodium acetate, okay, so therefore this one should be, again, this can another equation which holds true is the moles of acetate plus the moles of acetic acid is equal to 1. Okay, and again we can substitute this equation for the second equation, so we're gonna get 1.8 number of moles of acetic acid plus number of moles of acetic acid is equal to 1. Okay, therefore the number of moles of acetic acid, okay, that we need to produce should be equal to 1 divided by 2.8, which is equal to 0.36 moles of acetic acid that we need, which must again come from 0.36 moles of HCl gas. So to prepare a buffer of pH 5, add 0.36 moles HCl gas, and let's complete the sentence this time, to 1 molar and again 1 liter sodium acetate or acetate ions. Okay.